Thank you, John. So yeah, I can give do you guys want to wait like one more minute and then I'll do a little introduction? Who else is here? Let's see. Hi, Grace.
Hello, hello. Class just ended.
Yeah, I think some people have class. Well, Ryan's class was till 4.
Grace is sick of me by now.
Yeah. Oh, Alana, nice background. Maybe I should, let's see.
I was in class the other day and my professor was like she studied sexual development and like hormones and stuff. So she was like, "Are those sperm?" And I was like, "No, they're neurons." And she was like, "Oh, sorry, that's just like immediately what I see." So now I get like super self-conscious every time I use it. But they're neurons.
Yeah, they look like neurons to me if that makes you feel better.
Thank you. I appreciate that.
All right, let's start, I guess. So, hi, everyone. My name's Gina, for people who don't know me. I am the VP of Career Development for GSA this year. Oh, Olivia's here. Yeah, I'm a third-year BMP student, and I guess you could say I'm kind of biased because I am considering a career in academia. So this semester, I kind of wanted to host a bunch of seminar series for students who are thinking about pursuing a career in academia. And then with the current COVID situation, I also wanted to help out the first year graduate students who are looking for rotation labs, because I know my year we had like a mini retreat where professors kind of talked for 10 minutes about their research, and the first years didn't get to have that. So yeah, and Matt and Ryan here are new faculty. They both joined Jefferson less than 5 years ago. And I thought it'd be really great to learn more about their past experiences, what they're working on, and take a step back and kind of learn about how they both got here and what they're doing now. So yeah, thanks for volunteering, guys. Really appreciate it. And I'm excited to hear about what you do.
Okay. Well, thanks for the introduction and the invitation. And of course, I'm pleased to speak. Feel free to interrupt me at any time if you have questions, particularly related to the science. If you have questions related to kind of career stuff, we thought maybe we'd take that more like as a panel after both presentations. But okay, so today I've charged with giving kind of 2 parts of a talk. So I'm going to give a brief overview of kind of what we do in the lab and discuss some science without getting into too much details. Of course, you're welcome to ask questions. And then I'm going to give you some biased opinions about academic careers and kind of the 2 big transitions going from being a graduate student to a postdoc and going from a postdoc to a faculty member. And hopefully that's useful for you guys. Okay, so in my lab, we're interested in the response of the skeleton to mechanical force. This is because we study bones, and bone tissue is susceptible to fatigue, which is where really an overuse injury, in which repetitive loads that wouldn't normally break your bone lead to the formation and propagation of cracks. And so these things, sometimes called stress reactions, are stress fractures. They're painful, they're debilitating, they occur regularly, and particularly people that are physically active. So think soldiers, athletes, dancers get a lot of stress fractures. They actually at Rothman Institute, they have a time of the year they call it Nutcracker season, because it's when all the ballet performers start practicing for the Nutcracker. and they go from being relatively inactive to very active, and they all get stress fractures. So it's actually quite common. However, in general, mechanical loading is actually very good for your bones. And so it's a unique stimulus that can rapidly produce new bone precisely where you need it. The big example of this for many years now is a 22-year-old study now where they looked at elite tennis players that have a tendency to use one arm much more regularly than the other arm. And when they quantified the bone mineral content, that's the actual amount of mineral in the bone, you can see it's much higher in their dominant arm than their non-dominant arm. And this is not the case for your average Joe like you or I. And so loading will let you put new bone tissue right where you need it, which happens to be the position of maximum strain. So in our lab, we use animal models to look at this, different animal models of mechanical loading, generally mice and rats. These are actually images of rats, but we primarily use mice now. For the record, if you ever have a choice between mice and rats, you should go with rats. They're bigger, but they're much nicer, and they're friendly. Anyway, so what we can do with rodents is we compress their forearm using custom fixtures and a kind of a standard material testing system, and this generates both axial compression and bending, which leads to a position of peak strain at the mid shaft of the ulna. And so if you look at cross sections of a rat ulna following different kinds of load, you can label the new bone that forms, and this is what we see. So using a non-damaging mechanical loading waveform, you can get this nice ordered deposition of bone at the periosteal surface. Or we can generate a crack, as you can see the kind of right here in those green area here, and that leads to exuberant new woven bone, which is not well organized, but is analogous to a stress fracture in humans. So we can either get kind of a nice response to load or a poor response to load. So in our lab, we have kind of two main divisions of labor. We study sensory nerve signaling and also NSAID. So I'm just going to kind of briefly touch on both halves of the lab. So the reason that we're interested in sensory nerves in bone is because mature bone is in fact richly innervated. And this has not been appreciated very well in orthopedics for until in the last 5 years or so. It's really gotten a lot of interest. So sensory nerves are present at the periosteal region, but they can also extend down through bone into the deep tissue known as trabecular bone, and are even present in the compact mineralized bone in its sites of mineralization. But for the most part, they're present kind of in the outer layer of bone. And they're also specialized. So unlike sensory neurons, say, in skin, the sensory nerves in bone express TrkA almost 80%. Some say even higher than 80%, whereas in skin, it's about 30%. And so you may be wondering, what is TrkA? Well, TrkA is the high affinity receptor for nerve growth factor, or NGF. So NGF is most well known for being half of the 1986 Nobel Prize, showing that NGF can rapidly induce neurite outgrowth, here shown in sensory nerve from chick embryo, but in general is a very important developmental role and is strictly required for sensory nerve and sympathetic nerve survival. Postnatally, it is involved generally in neurotrophic signaling. Because we're not really that kind of lab, I'll just be discussing NGF signaling through TrkA, although in full disclosure, it's kind of a complicated system. And so we wanted to know if there's a role for sensory nerves in the way that the bone responds to load. And part of the reason for this is that the nerves are just in the right spot. So if you look at a rendering of sensory nerves on the surface of bone, you can see that they cover the bone kind of in this mesh or net. And that's where the position of peak bone strain is, and that's where new bone forms when you load it. And so some other group, this is Marylene Vandermeulen's group at Cornell, they did kind of an unbiased RNA sequencing study looking at bone that was loaded. Here, they actually used tibia, but it's the same kind of idea. And what they found is that nerve growth factor, or NGF, was one of the most highly upregulated genes in both the compact cortical bone and the trabecular spongy bone. And so, so this got us thinking about whether or not NGF really played a functional role in the response to mechanical loading. We've done a variety of studies in this area. I was going to kind of summarize what we're interested in now. And so what we've shown is that osteoblasts, which are the cells on the surface of bone that are responsible for producing new bone tissue, express NGF in response to load. And so we want to know how NGF expression is regulated in the osteoblast, what kind of osteogenic cues that sensory nerves can provide to support bone formation. We're investigating the use of TrkA agonists, so non-NGF type of molecules that we can use to leverage the signaling system to decrease stress fracture risk, for example. I should say that NGF itself is a failed drug, so it was used in the 90s as in order to try to prevent some of the side effects from HIV and diabetic-induced neuropathies, and actually is quite effective, but has a lot of side effects, namely hyperalgesia and sensitivity that patients basically don't like. And so we're looking for other kind of ways to leverage this system. And in general, we're also interested in the role of NGF TrkA signaling in dental implant osseointegration and this concept of osseoperception, which I won't get into here, but this is the idea that you can feel through implants, both in traditional like hip and knee implants, but also through dental implants in your mouth. Getting kind of sensory information through them is fairly important for quality of life. And so we're interested in that as well, and the role of NGF in that process. And then the other half of the lab is basically interested in NSAIDs. So these are non-steroidal anti-inflammatory drugs, and specifically their role in stress fracture risk. And so the reason we're interested in these is NSAIDs are the most commonly consumed medication in the world. About 30 million daily users of NSAIDs in the US, and that's going up. And in particular, about 80% of active duty US military take NSAIDs every day, that's basically everyone. So, so we're interested in them because we're interested in stress fractures, and soldiers get a lot of them. So NSAIDs reduce pain and inflammation by blocking either COX-1 or COX-2 or both. And these are the enzymes that convert arachidonic acid downstream into prostaglandin products, particularly PGE2, which acts in bone. And NSAIDs are not created equal. There's selective and non-selective NSAIDs, reversible and irreversible binders, and a lot of different chemistries. Most of these drugs are not designer drugs, so they were produced kind of like by trial and error to determine if they had an anti-inflammatory effect. And there's a kind of a newer generation of drugs that is more of a designer drug, the COX-IBs, which specifically inhibit COX-2. If you look at stress fracture risk in U.S. Army soldiers, you see that that the risk goes up if they take an NSAID. Any NSAID was associated with about a 2.5-fold increased risk of stress fracture, with naproxen having the highest risk and aspirin having essentially no risk. And so this led us to hypothesize that there may be a difference in the way that naproxen and aspirin act on the skeleton. And so we did a variety of studies to look at this. I'm just going to show a few results. This is work done by Gino Park in my lab. We published it last year. What he showed actually was that naproxen, but not aspirin, had a particularly deleterious effect on femoral toughness. And so this is the amount of energy that you need to put into a material to get it to break into two pieces. And it's kind of best illustrated here by this 3-point bending graph, where the y-axis here is the force and the x-axis here is displacement. You can see as you kind of go up this graph, these three bars look very similar, with vehicle in black, aspirin-treated bones in red, and naproxen-treated bones in blue. And this is where you spend most of your life, is down here in the elastic regime, where you load your bones, they bounce right back to where they were. But as you transition into the plastic regime, where you start putting damage into the material, you can see that the vehicle-treated bone and the aspirin-treated bone can deform quite a bit before they break. But the naproxen-treated bones, for some reason, they don't last as long, and they fail in brittle failure relatively quickly. And so we've been investigating this phenomenon. We initially chalked this up to differences in collagen thickness, as shown here in these picrocereus red stained cross-sections of femurs. You can appreciate that the naproxen-treated femur has a lot more green and yellow fibers and less red ones, suggesting that those fibers are thinner, and that may contribute to the decreased toughness. More recent work in my lab by CBRM student Sandra Chuchu has shown us that naproxen treatment also seems to affect the osteocyte dendritic network in bone and decrease perilacunar remodeling, both of which are associated with diminished toughness in bone. It may suggest kind of a non-COX-2 mediated effect of naproxen directly on bone cells. And so we're looking into that. I should say she's looking into that. I'm doing very little. Okay, so that's all I'm going to talk about with regards to the science. So that's kind of what we study, bones and bone stuff. I'm now going to transition into talking about some of the career stuff for a few minutes. unless there's any questions related to bone science. So, so I have a couple disclaimers in talking about whether or not the academic path is right for you, or for me for that matter. So my disclaimer is that I was a postdoctoral fellow in 2016, which is not that long ago. So, so I have fairly recent experience in this area in terms of being a postdoc and in general being a trainee. The con is that I have fairly narrow experience in this area, N of 1. So you may want to take my advice with a grain of salt. I love my job, which my job obviously is being a faculty member. So hopefully it means I can give you some good advice. The con is that I recognize that there are other options in life and in science for that matter, and that the academic career is not the career for everybody. It is for me, but it may not be for you. So, so how do you figure out if the academic path is right for you? Well, I think an important thing to do, in particular for if you want to be a faculty member, is think about the things that you do well. And you also want to think about the things that you enjoy doing. So if the things you do well are academic and the things that you enjoy doing are academic, then that's a good place to start. You also want to consider the things that you do poorly. So if, for example, you don't really like writing, you don't really like lecturing, you really hate public speaking, and you can't stand other students, then an academic career might not be for you. So the things you enjoy doing ought to line up. So these are the areas that you want to avoid, is the overlap between things you may do well, but that you don't enjoy, and things that you enjoy, but you don't do very well. And if an academic career includes the things that you do well and the things that you enjoy, then it might be a good choice. Okay, so transition 1, thinking about going from being a graduate student, where you may be now, to being a postdoc, is a really important transition. And so if you're and particularly if you're interested in an academic career, it's a real pivotal transition for you. Some kind of notes that I might think about. The first thing is you do have an opportunity to change your research topic. So particularly as you kind of are wrapping up your graduate student career, you've invested quite a bit into a really narrow area of science and learned quite a bit in that area. So not to discount that. But if you're interested in changing kind of what you study, that's a good opportunity. And you can switch fields entirely. So, you know, you may be studying cardio now, but you're really interested in neuro. You can certainly think about doing that. And I'll kind of talk some more later about career arc, but that's an opportunity for you. And generally speaking, you're going to change location or change your university. You don't necessarily have to, but that happens a lot, and for good reason. So part of it is your best opportunity, maybe someplace else, but also it's good to expand your network, meet new people, meet new faculty members, and really expand kind of your knowledge base. So I recommend it. I would also note that a lot of times graduate students don't recognize that they're in demand. So, so being a well-trained graduate student and graduating with, particularly graduating well with multiple papers, you're going to be able to, it's not going to be challenging for you to get multiple offers. So, so how should you pick a postdoc mentor? That really the ball is in your court about who you want to pick and what you want to study next. And that's related to the research topic and related to location/university. But there's really kind of two choices. One is kind of an old or established mentor, and one is maybe a younger or more motivated mentor. And there's kind of pros and cons in both of those categories, and maybe we can chat about it later. In terms of my story, so I did my undergraduate and really graduate research in bone, and started out in a mechanical engineering lab and went to a more in orthopedic surgery, but biomedical engineering undergrad or graduate work. And when I went to find a postdoc, I was interested in trying to get more molecular biology and cell biology, because my background was really more animal work and engineering. And so that was really my goal, was not to necessarily change fields, but to change, to kind of like add to my skill set. And my PI as a postdoc was an older, more established mentor. And the reason for that was I basically wanted to try to establish a new kind of network and think about going into academia. And an old established mentor is can be more advantageous for that. Isn't always, but can be. And I will say that my story, kind of my academic trajectory, is very traditional, and yours may not be like as traditional as mine, and that's okay. So that's something to think about. Okay, so transition 2 is going from postdoc to faculty. This is a little more fraught. So so when you're a graduate student going to a postdoc, that's a little, you're kind of in demand. When you're a postdoc going to a faculty position, particularly like today, because like COVID and all that kind of stuff, but just in general is more of a fraught transition. So the first question to ask yourself is are you ready? There's really no clock on being a postdoc, particularly now. Maybe there used to be, but a longer postdoc is not like a red flag. So you do want to think about when you're ready to kind of go in the market. And the two things for me that you might want to think about are publications. And generally speaking, you're going to be competitive for a faculty position with more than 5 first author publications. That's a kind of a good benchmark. That's not true for everyone, but if you're in that category, that's a good place to be. And also, you really want to have the support of your mentor, preferably it's someone who's established and is really rooting for you and is in your corner. But you need someone to write you a strong letter, or 2 or 3, so that the committee is interested in you. You do want to think about what type of position you're looking for. So things like how much research, is this an R1 university? Am I expected to teach? What's the service requirements? Are there any specific requirements that I need? For example, I need to have an animal facility, or I need to have clinical collaborators, or I need XYZ, or are you open to kind of seeing what's out there? And I would just note that in general, a faculty job is like buying a house. So you don't need to buy every house on the market. You just need to buy one. So you want to find the one that you like. So a typical faculty application includes a lot of things, which I'd be happy to discuss if anyone has any specific questions on these. And I would just kind of note that they're not necessarily of equal importance, and that your research statement and your professional references are generally more important. So I want to offer you top 5 random pieces of advice, and then maybe I'll pass this to Matt. So the first thing is that your application is going to demonstrate your overall theme and trajectory of your career. So this is really starting from your graduate studies all the way through the end of your postdoc, is this idea that I've been thinking about how to put together my my research and my career to get myself ready for a faculty position. So thinking about that idea of whether or not you're going to change fields or change emphases at your postdoc position is part of painting this picture of, yeah, I've been, I'm headed towards independent research. You want to exceed the minimum requirements. So thinking about things like publications, accolades. Do you need a K99? Comes up a lot when postdocs ask me about getting a faculty position. And my answer is always the same, which is it doesn't hurt. It's not strictly required, but it doesn't hurt. You want your application to be exciting but readable, because readers are going to be unlikely to be in your specific niche area. So you do want to think about having someone outside your area read your application. You want to paint a picture of a realistic 3 to 5 year independent research program, with this idea that your research statement is basically a grant. And you want to be able to ensure the satisfaction of any specific requirements that you may have. And that includes also the requirements that the hiring committee may have of you, which may or may not be included in the job description, which is kind of bogus, but it happens. So they may be really looking for like a fly person and not interested in a worm person. And that's not going to go in the application, but that's just the reality. They only want fly people. So something to consider. And there's not one right way to put together applications, but you should start thinking about it at transition number 1, going from a graduate student to a postdoc, about how you're going to paint yourself as a faculty member, and get somebody else to read and comment. I would note that even very strong candidates are rejected repeatedly, which is the case when you're applying for a faculty position, and definitely the case when you are a faculty member, because you'll have to start putting in grants. and the rate is low. So this is good practice. I would note that you usually do a Zoom interview before on-campus interview, and after you get an interview, you can expect that about a third will make an offer, thinking about basically top 3 candidates. And there's also job offers that come in a variety of flavors, mainly like written offers versus what I call a soft offer, or kind of a verbal offer. So in terms of my story, so a potential scenario is you may apply for 40 positions. You may do 8 Zoom interviews and 3 campus visits and get 1 written offer. So if that doesn't sound like a lot of fun to you, then maybe like a faculty position is not like necessarily what you want to do. I would say it's not vastly different than applying for, say, industry positions. It's just kind of a different scenario. So in terms of my story, I had a very similar kind of trajectory to what's shown here. I applied mainly to places like Jefferson, so academic medical centers. I was interested in being in a orthopedics department because I study orthopedics, and needed to be somewhere with an animal facility and needed to be somewhere where I had access to clinicians. And Jefferson ended up being a really great fit for me. We have a top orthopedics department clinically, and also a lot of research activity, and kind of a minimum of requirements outside of research. So that was really very appealing to me. It's just why I kind of ended up here. So anyway, I guess I'll stop there, and hopefully that was helpful. And I'll stick around till Dr. Schiewer is done. Ah, so close.
Thank you. That was great. I appreciate your honesty.
Of course.
So I guess, were there any burning questions about the science before I start my spiel from anyone? It's a resounding no.
I don't know. It's just a bunch of names and boxes for me. So
Yeah,
there's no guarantee anyone's out there.
I'm trying to share my screen right now. Okay. There we go. Does this work now? I haven't had to share my screen yet, amazingly.
Great success.
Can you see it?
Yes.
Excellent. Okay. And there we go. Is that full screen, or you see it as the slideshow presenter thing?
It's the presenter thing.
Okay. I'm not that old. I shouldn't be this technologically disadvantaged. Oh my God. All right, I'm going to turn off my two screens. Maybe that'll help. Maybe that's why it doesn't like me. Okay. Eh?
Oh, it's fine. I've seen it like this before.
Hey, Matt, Dr. Schiewer, go to swap display on the left corner.
Ha!
Look at this guy.
All right. Well, show me up. Okay. So I think I did the requests for information in order. So my path to here was I did my bachelor's degree at a small liberal arts college in Indianapolis called Marion. I did that in 2003. When I went to school, I thought I was going to go to medical school, but due to circumstances that were largely my fault, I did not qualify for medical school. And then being in Indianapolis, I thought I'd work at Eli Lilly with my bachelor's degree. I also have a family history there. My maternal grandfather and one of my uncles worked there, but they said no thank you to me as well. So instead, I got to do some horrible quality control chemistry jobs and waited tables for 4 years. And I tried to apply to graduate school a couple times within that period of time. And then eventually I got into the University of Cincinnati, into the PhD program in cell and cancer biology. And I was there for only 1 year. I did 2 rotations. My second rotation was with Dr. Karen Knudsen, who some of you may know, who's now at Jefferson. And actually when she moved from Cincinnati to Jefferson, she brought me with. And so I completed my PhD in the genetics, what was the genetics program and is now called Genetics, Genomics, and Cancer Biology, from 08 to 12. And funding during that time was a DoD pre-doctoral grant. I did a minimal transition to a postdoc within the same lab, within Karen Knudsen's lab. I did that for 5 years, and I was funded by the Prostate Cancer Foundation during that time. I made an even smaller transition, or maybe not smaller transition, but just a transition. I remained in the same lab. The title changed. This is non-tenure track faculty, research instructor. I did that for 2 years, and I was promoted again by the Prostate Cancer Foundation. And then November of last year, I started my own lab at Jefferson. Funds are coming from my startup funds, which are provided by the institution. I have a, that should say Commonwealth of Pennsylvania, not State of Pennsylvania, grant, which is part of the tobacco settlement funds from Pennsylvania. I have American Cancer Society pilot grant award and another pilot award from the Philadelphia Prostate Cancer Biome Project. So the transition, the previous speaker talked about changing institutions and how that's the typical way of things are going. I'm very atypical the way that my path led, but I still have ideas and I'm happy to talk about them, but I didn't break things down in the same manner that Ryan did. I'll just get into the science real quick. So my lab's interested in prostate and bladder cancer. My training in the Knudsen lab was all about prostate cancer, but I decided to start looking at bladder cancer as well. And that there's a lot of reasons for that. One of them is that the catchment area for the Sidney Kimmel Cancer Center has a higher both incidence rate and mortality rate for bladder cancer than either the state of Pennsylvania or the United States as a whole. This is also true for prostate cancer and other tumors, but as a faculty member in the Department of Urology, I'm going to stick in the GU space. Specific directions in the lab. So in bladder cancer, we noticed in some of the patient level data within the cancer center, in purple are patients that have both, are men with both prostate and bladder cancer. And in teal are patients, men specifically, with just bladder cancer. And so the teal patients were receiving therapies directed towards the androgen receptor, and they had 2 tumors, and they did better than those patients with only bladder cancer who were not receiving the anti-androgen. So it's obviously not a straight line from bladder cancer is a decent treatment target in bladder cancer, but what we're trying to do is develop it as such. And so to do that, we're trying to look at, right now, it's just a black box of what the androgen receptor does in bladder cancer, as far as I can tell from the published literature. So Ryan mentioned a research program, and this figure is actually out of that, research statement. This is part of my research statement when I put in my application to be an assistant professor. And so part of what I hope to do in my lab is to develop an understanding of the consequences of the androgen receptor function in bladder cancer, what genes it might regulate the expression of, the molecular mechanisms that drive AR function in the context of bladder cancer, and define the context in which AR is relevant, meaning which molecular subtypes or other sort of both cell autonomous and non-cell autonomous contexts in which error is relevant. There's actually quite a bit of deregulation of both androgen receptor signaling and androgen biosynthesis in bladder cancer. So this was, if you're into cancer, you should know about cBioportal. And if not, I'm happy to teach you about it. But within that, there's a plethora of alterations. So we plan on modeling that and seeing if patient-derived alterations in these pathways impact biology and response to therapy. And then finally, in AIM 3, we're going to functionally assess whether targeting the androgen receptor is a thoughtful way of trying to attack bladder cancer. And just a little snippet of data. So we got hold of a tissue microarray for bladder cancer patients here at Jefferson. One thing about the disease that also led to us wanting to look at sex hormone signaling was that it's much more frequent in men, which holds true in this TMA, 114 versus 43 than female, but females tend to do a lot worse than men. But we got this tissue microarray from Jefferson patients, and we stained it via immunohistochemistry for the androgen receptor. And then we had a pathologist score it. You could see that roughly 50% of these tumors are negative for the androgen receptor, but in both male and female tumors, they're about 50% positive. And the extent or the magnitude of expression of the androgen receptor is similar between male and female. So it looks like sex is not a determinant factor of AR status in bladder cancer, but very early days. If you're trying to start a lab, I would recommend not doing it a couple months before a pandemic.
Okay.
So another avenue in the lab is sort of building off some of the stuff I did as a member of the Knudsen lab. So very interested in a DNA repair enzyme called PARP1. And what we previously found was that both the enzymatic activity of PARP1 and the way in which it regulates transcription are elevated as a function of prostate cancer progression. And the way we think about it is that PARP sits in its canonical DNA repair complexes, leading to altered DNA repair and enhanced tumor cell growth and survival. But based on our previously published work and some stuff that's coming down the pipe, it looks like the transcriptional regulatory events that are under the control of PARP are also elevated as a function of prostate cancer progression. And we've gone on to characterize some of these pathways, but there's still other things to look at. This includes cell cycle genes, DNA repair genes, androgen receptor targets, and the like. And through this arm, PARP leads to enhanced DNA repair factor availability and oncogenic signaling, leading to tumor cell growth and survival. So a little bit of data. Forever ago, it seems like we did a pretty simple experiment where we put hormone therapy sensitive prostate cancer tumor cells into immunocompromised mice. And then we randomized these mice into 4 treatment arms. Black is our control. The dotted gray line is castration. This is to mimic androgen deprivation therapy, which is the standard of care for metastatic disease. We hit one cohort with PARP inhibitor, which is in green, and then the red is the combination thereof. So from this graph, you could see that castration and PARP inhibition, the lines are almost superimposable, suggesting that they have similar efficacy. But if you put them together, you get this at least additive effect. And in fact, over the 60-day treatment course that we did, 20% of these tumors never doubled in size, suggesting that the combination of PARP inhibition plus castration therapy leads to a blockage of the transition to castration resistance. And that's important because castrate-resistant metastatic disease is the lethal form of disease. So again, we did some tissue microarray studies. We got our hands on some primary prostate cancer, meaning it's still localized into the prostate, and we got our hands on some metastatic castrate-resistant disease. Again, this is the lethal stage of disease. We developed a immunohistochemistry assay to look at the enzymatic activity of PARP1, that being PAR, and we had a pathologist score that. And here you can see that there's more PARP, there's higher PARP activity in advanced disease than there is in primary disease. So I've mentioned briefly that PARP regulates transcription, DNA repair, and another thing that it seems to be involved in is chromatin architecture. So this is previously published. I forgot to add the citation, but I'll walk through this real quick. This is a micrococcal nucleus sensitivity assay. Use this it's an older school method to look at chromatin accessibility. So if it's above 1, it's more open. If it's below 1, it's more closed, the chromatin, leading to differentiability for transcription factors to bind and do their thing. So control in black, DHT should open chromatin at this canonical androgen receptor. DHT is an androgen, dihydrotestosterone, at a canonical AR target gene, and we see that it does, but this is not abolished, but diminished by PARP inhibition, suggesting that PARP can counteract the ability of some things to alter the chromatin architecture. So we want to expand this and look just genome-wide in the context of prostate cancer. Like, what is PARP doing to chromatin genome-wide? What does targeting it pharmacologically do? Because these PARP inhibitors are FDA approved for a number of tumor types, and in further clinical development for a number of tumor types, including prostate cancer. And then there's not really that much known about what is the chromatin state of GU malignancies, in this case, prostate and bladder. So we're going to look at that. And to do that, we're going to use this kind of cool system where, since I'm in the Department of Urology, it's really nice. I have pretty ready access to surgical specimens. So one of the mainstays of treatment for localized prostate cancer is prostatectomy. When a gentleman gets his prostate removed by our urological surgeons, they let me know and I get a portion of it. I bring it back to the lab, I subdivide it, and culture it as an explant. And to do this, we put our little 1 millimeter cube pieces on top of a veterinary wound healing sponge. And this allows for us to feed the tumor pieces through capillary action through the cube. And you can put drugs in there, you can do shRNA, you can do all sorts of stuff. And then on the other side of that, you could do all sorts of molecular stuff. So here we just hit it with a PARP inhibitor and we hit the target. Here's the enzymatic output of PARP. It's positive here in the control and it goes down with the PARP inhibitor. And this was associated in this model system with decreased proliferation, which was sort of nice to see based on our previous, in vivo data. Some of the cool aspects of this sort of system is that it maintains the glandular architecture and other salient features of the original tumor. So you've got stroma in there. While I'm not an immunologist, I know that there are immune cells in there that could be characterized. The tissue microenvironment, there is some innervation in there if you're into that, like Ryan is. So this is a pretty powerful tool to take actual human tissues, manipulate it in the lab, and be able to do molecular readouts. So a third arm, I'm only going to do 3. A third thing that we're kind of doing in the lab is taking trials that we've been involved with, their the preclinical rationale for them, as well as writing up some of the correlative studies. So this is one of those trials. This is combining the PARP inhibitor niraparib with radium-223, which is kind of a cool drug. It's a radioisotope that kind of looks like calcium, and as such, it has a propensity to go to bone, which is important for metastatic prostate cancer because the majority of metastases in prostate cancer are at bone. So this is taking a radioisotope to the site of the metastases, emitting alpha particles and causing DNA damage. So the idea here is we're causing DNA damage with the radium-223, and we're trying to block DNA repair with the PARP inhibitor. But I already told you that PARP does more than DNA repair. Anyway, so just 1 second. So the results of this is a very small phase 1b. Because since it was a phase 1b, the primary endpoint was to find the maximum tolerated dose, and the phase 2 dose will now be 200 milligrams of the niraparib. what's kind of interesting is you had the readout for response was either a decrease of at least 50% in PSA or prostate-specific antigen. You might have heard of that, which is a direct AR target gene, or at least a 30% decrease in alkaline phosphatase. No patients that had received prior chemotherapy responded when PSA was the readout. 40% had an alkaline phosphatase decline. And so it seems like there's an enrichment of chemotherapy naive patients in responders. And these same two readouts I just talked about, PSA and alkaline phosphatase, here they are in waterfall and line graph, and the colors correspond to the same patient. So this green patient responded well when you looked at PSA, and he did pretty good when you looked at alkaline phosphatase too. But this patient did horrible when the readout was PSA, but really well when the readout was alkaline phosphatase. And so what we're trying to do is to take the specimens that were collected during this phase 1B and into the phase 2 and perform reverse translational science. So we're trying to find biomarkers of response resistance to this novel combination of PARP inhibition plus radium-223 and define the mechanism of action of combination. One thing that I didn't show here is that we do have some preliminary genomic sequencing data from these patients, and none of these patients harbored alterations of BRCA1 or BRCA2, which tend to enrich for patients that respond to single agent PARP inhibition. So the mechanism of action of this combination might be slightly different. So that's the science. So for the application process and the fit with Jefferson, it's very different than what most people will have when they go to try and find a faculty position. So I've been at Jefferson since 2008. I was a known entity for a number of faculty members. I'd interacted with basic scientists, translational scientists, and clinicians. And it felt like if I had gone somewhere else, I would have lost out on the goodwill that I'd already built up. And there was also an interest in keeping me on. So it just sort of worked out. And I know that a lot of job talks or, career talks, how did this happen? Right place, right time. I think that's unfortunately for you, the viewer, but me as a person, it just worked out. As far as fit goes, the application process was exactly the way Dr. Tomlinson outlined. CV, letters of recommendation. I had to put together a research plan, no deviation from that. So that was all the same. The transition from postdoc to faculty was kind of weird. So my PI was super generous with giving people autonomy to function. And I won't say that I was fully functioning as a postdoc as a student, but I was doing a lot of things that postdocs do. And then as a postdoc, I was doing a lot of things as a junior faculty was doing. But luckily, I was able to do it more formally in the transition, because then I could be more involved in managing the lab, becoming even more independent and applying for independent funding. So it's very non-traditional. So but I'm happy to answer questions. I have opinions on things, but it's a very non-traditional way of doing things. I was asked to touch on a healthy work-life balance. I don't think that's a thing. I think work is part of your life, and I don't think they're necessarily in opposition to each other. Like, I think you have to find a way to, like, my job, I love my job. It's part of my life, and I derive value from it. So trying to separate it's difficult. Although here in COVID times now, I do have to put up like actual barriers, because my wife is a self-employed entrepreneur. So she's already had an office set up, and I'm relegated to our basement spare bedroom. But we have to text each other, even though we're in the same house, to be like, hey, are you working right now? Is it okay to talk? That sort of stuff. So that's an interesting way to try and do work-life balance. But you could work too little, you can work too much. Neither of those are good for you or your career. But I think it's a bit of a fallacy to say that work-life balance is a thing. But that's probably easier for me to say because we don't have kids yet. And my training helped to prepare me as a PI because it gave me, Dr. Knudson's a great boss. She gave plenty of room and resources to develop ideas, which is really like what's going to really help you as you go forward is time and resources to develop ideas and do the go, no go experiments that will allow you to develop a research program. Tips for a smooth transition: if you have the opportunity to develop preliminary data for grants while you're still in one position or another, either from the transition as a graduate student to a postdoc or a postdoc to faculty, you really should take advantage of that. Of course, that has to be explicitly given to you by your PI, but if it's given to you, take advantage of it. Don't look at, because it doesn't matter which transition it is from student to postdoc or postdoc to faculty, it's going to take a while to get ramped up. You're not going to hit the ground running regardless of what you think. Hardships from the transition, there were zero hardships in the transition from student to postdoc, from postdoc to faculty. It's weird that so many people do that, but it almost feels like you have to reinvent the wheel each time, figuring out where things are, who to talk to about stuff. It's very strange. Where did Zoom go? Sorry. So take the time that you're given. I guess that's really it. And I think we should just do questions now. I might be better at answering questions than I am at talking.
Yeah, that was great. Thank you. Do you want me to start sharing my screen so then it stops yours?
Yeah, I can't. I'm really sorry. I'm done.
Oh, it's okay.
Stop share.
Oh, you got it.
Hey, look at me. I can find buttons.
Okay, so questions. Who has some questions?
I was wondering for both professors, how many people you guys have working in your lab currently, and how your lab has dealt with like the shift works, if you guys are doing that.
I'll go first since Dr. Tomlinson muted. So we my lab just started last November, and right now it's just myself and a technician. And shamelessly, I'm going to put a plug in. I'm looking for postdocs and students. So if you're into either translational or molecular cancer research, come on down. Talk to Hannah. She knows how I am. She rotated with me.
Yep, it's true.
So the way we dealt with it is pretty easy because there's only 2 people. I have a full lab as far as square footage goes. So socially distancing for the 2 of us is not difficult. Sometimes we want to get in tissue culture at the same time, so we can't do that. I've said that that's not okay. Even though the tissue culture room is huge, I don't want to run that risk. But it hasn't been a problem for me. But again, my situation is unique relative to others.
Yeah. Well, so I'll answer your question in a couple ways. So the first thing I'll say is when I started, that's actually probably the biggest transition from being a postdoc to a PI is having to hire people. And hiring people is difficult, and recruiting is difficult. And Matt gave a great example there, which is that you're always be hiring and recruiting. Because that's actually a very challenging part of going from PI is getting good people, because good people drive good science, and getting good people is challenging. So my lab is I have 2 technicians, a postdoc, 2 graduate students, and and we shut down basically on March 16th for kind of a hard shut off of basically everything. We're a very wet lab. We don't really do computational stuff, or most of the work we do is animal work, and not even a whole lot of in vitro work. So we were off probably for the most part for a couple months, and kind of started coming back in June with a calendar, and just trying to keep a limited number of people in the lab at a time. And I will say in the last like a month or so, maybe 2 months, we've been more or less back to normal. I'm not in as much as I'd normally would be in, because there's no reason for me to just sit in my office. But I teach in the medical school, and they started back in July, and that's in person. So I've been around kind of.
I have a question, unless anyone else has a question.
Sure.
So this is to the both of you. It's pretty much based on the transition from a PhD student to a postdoc. So Matt, my understanding, you pretty much stayed in the same field because you stayed in the same lab. Ryan, you kind of switched a little, switch gears because you went from a engineering lab to more, I guess, cell biology. So how did you, also in terms of independence as a postdoc versus a student, maybe not so much hands-on from your PI, but also was it difficult to, I guess, switch topics a little bit, in terms of keeping with the same topic of your PhD research?
Yeah, so I've talked to a few people about this actually, because I think this fairly universal experience for people, particularly people that change geographies between graduate school and postdoc. So when you're a graduate student, you're a senior graduate student in a lab, you have a lot of institutional knowledge. You know where the bodies are buried. You know how the experiments are run, what your PI is like. You're a functioning member of society. And then you move to being a postdoc, and you don't know where anything is. You don't know what the experiments are. You don't know what the model system is. It's a very humbling experience. Even though you're you have a PhD, all of a sudden you're back to being a low man on the totem pole, and eventually that is not forever. That's a short term. But that happens particularly if you change locations, because you also have to deal with kind of the life realities of you have to find a new place to live, figure out where the supermarket is, all that kind of stuff. And so that's a fairly large transition. Scientifically, you're just gonna be lost for a little bit. I was lost for, my first year of postdoc was not super productive. So I got better after that, but first year I was not super productive. So I don't know if that's a good model or not. I'm just saying that's what happened for me.
It's very realistic, I would say.
No, and to that point, I myself didn't change labs or change fields, but I've seen people change labs and change fields into the lab I trained in, and that occurred with everyone. It's a learning curve, irrespective. So that transition, you go from big fish, small pond, small fish in whatever size pond, and it happens again in the next transition as well. You just have to set yourself up to change the trajectory of the curve in each instance. And if you're given time to think deeply, do so.
Yeah, I would say kind of something that Matt touched on, and I intended to touch on, but I forgot to, was I have a general rant about the K99, which I won't subject you to unless you really want to hear it. But I suggest it to postdocs, not necessarily because I think it's a good award, but because part of the process of writing that grant is that you have to have a discussion with your PI about what you're going to do when you leave the lab, and they have to sign a statement saying that they agree with that plan and that you're going to do this and that they're going to do this other thing. And that's actually very helpful, even if you don't get the award, that you have that plan of, when I leave the lab, this stuff is mine and it's independent, which requires you obviously to think about what's the stuff that's going to be yours and being independent. But that's a very valuable conversation. And so I recommend you do the award, even if you don't necessarily get it. It's very worthwhile to have that conversation.
as a person who tried for and failed to get a K99, it was a very good conversation to have, because it put everything in stark terms about what intellectually or even physically what reagents you could take with you. And any good boss should do that of their own volition, but having a little something to push that discussion as you transition is good too, because people are busy and they don't always think about it.
Anyone else? We can have time for one more question.
If no one else has a question, I have one. Go ahead.
What was it? I can't.
Yeah, I've got a question going like a little further back in the transition timeline. Forgive me, I'm out of breath. I'm out for a run. But can you talk a little bit about transitioning into being a graduate student, where you're now expected to like attend conferences and start building that pretty critical network and getting over the sort of intimidation factor that comes with that?
Yeah, that's a good question. You want to take that, Matt?
So I would say start small. You would be surprised how many faculty notice which students and postdocs ask questions in local seminars, and that'd be a good opportunity for you to try to break through that fear. And no one's gonna castigate you for asking a question that seems silly, because there's no such thing as a silly question anyway. I think it would be a point of pride for whoever your PI is to know that you're out there putting yourself out there in those things. So that would be the first step. The second step is to have a discussion with your PI to have them make introductions. Because if they should have been to these, they have likely been to these meetings before and they know people. And if you could get in that way, that's a valuable way too. And then outside of that, you should, I think, having a conversation with your peers, like other students and postdocs at like poster sessions, is useful. And then you might see them with their PI later, and then that is your entree into a discussion with the PI. But I think starting small and doing local will make it less painful in the future.
Yeah. So I'll add a couple things to that. Well, first I'll tell an embarrassing story. So first time I gave a talk at a conference, for bone people out there, it was ASBMR. I don't remember what year, but a long time ago. And it was at one of these plenary sessions, so it was like pretty fancy session. And I gave the talk. It was fine. In retrospect, it was probably not good, but at the time it seemed fine. And after the session was over, it was like, I think it ended at 5 or 5:30. I was hungry, and so I just booked it out of there, went to go get dinner. And my boss called me on the phone as I was leaving the conference center, and he's like, "Where did you go? You got to stick around. Like, I'm going to introduce you to people after your talk." And I was like, "Oh, I didn't know. Like, what do I know?" So you want to lean on your mentors to introduce you to people. The other thing I will say, just kind of generally, is that this idea of building a scientific network, it is super important, but it doesn't need to be super inorganic. When you meet people that are your peers at conferences and just through other social interactions, that natural kind of organic network building does grow over time. And so you may only kind of meet one or two people at this conference or one or two people at next conference, but when you stick around, it's a long game. It's a marathon, not a sprint. And so that adds up and it becomes exponential, and eventually there's too many people to keep up with anyway. And I would say like the persistence counts for a lot. Just kind of showing up counts for a lot. So do things. Don't feel like I'm not sure how that's going to go, or I'm not sure what that's going to be like. Just show up, and that will go a long way. And I would say that my opinion is you should think about your peers as much as you think about like the big wigs in the field. who making kind of networking with your peers is just as important, and they'll stay in the field just as much as you do.
Second.
Any other questions?
No questions. Okay, yeah, I think we're over 5 o'clock as well. Yeah, I think you guys answered the majority of my questions as well during your presentation. Ryan, I liked your segment on like the number of places you apply to, how many interviews you get, the realistic numbers. It was nice to see.
Yeah.
All right, well, thank you everyone for coming, and thank you guys for participating. I hope everyone thought this was useful, especially for people considering a postdoc and going into academia. And yeah, I know both of these PIs are taking students, so any first years, send them an email if you're interested.
First.last@jefferson.edu.
Yeah.
You can contact and you can contact me for other reasons too.
I was going to say the same thing, which is feel free to email or hit me up on Twitter if you if with questions, or if you have something personal or whatever.
There's another way you can build your network, is Twitter. I'm terrible at it, but people do that. People are really good at that. I'm not one of those people, but I see it.
Twitter's for real.
Yeah, Twitter's for real. Not TikTok.
Not TikTok. Twitter though. John's on Twitter.
John's also on TikTok, so
I don't want to see him on TikTok. All right.
Yeah, I've been trying to get famous. It hasn't worked.
Good luck.
keep trying.
All right.
Well, thanks, guys.
Good luck. Thanks for having me.
Thank you.
See y'all.
Bye, everyone.